Good evening, class. Welcome to the course Electronic Theory of Solids. And in this is class 10 of Electronic Theory of Solids class. Theory of Electronic Solids. Yeah. So in today's class, I'll be discussing the problems which will be based on the magnetization. Writing down the partition functions out of the Hamiltonian systems, discussing different type of magnetism. So from these topics, I will be taking the questions, and out of those questions, you will understand the system well, and will also understand how to approach the problems with given parameters. So, having said that, I will start with the very first question. Question number 1, in which I'll be aiming on determining the partition function of the system with given Hamiltonian. So the question goes like, suppose you have a 1D ferromagnet with J greater than 0, let's see, and in the Ising Hamiltonian, so Ising Hamiltonian is nothing but summation over sigma I sigma j for a 3-spin system, a system in which it can have the 3 different spins, sigma 1, sigma 2 and sigma 3, that's what you can think, with periodic boundary condition. So your Hamiltonian H is nothing but minus j, where j is greater than 0, summation over ij and sigma I sigma j, where I and j are equals to 1, 2 and 3, because as I said, 3 different spin system, and ij denotes the nearest neighbor. Nearest neighbor. Then based on this, so the question which is main question out of it is, so till now this is the problem statement. Now comes the question. The question is, what is the partition function? Because if you know the partition function in the system, then using the thermodynamic analysis, you can estimate the entropy, you can estimate the free energy out of it, you, and you can estimate the magnetization. All those things you can do, but you have to first know the partition function. So that's what we will be aiming for in this problem. So what is the partition function of the system? So now comes the solution part. So for to estimate the partition function, first we will have to know the form of the energy. What is the energy? What is the degeneracy of that system? And knowing the energy and the degeneracy of system, you can easily estimate the partition function. So that's something I will also come to. So the system which we have is a 1D ferromagnetic Ising Hamiltonian. As I said earlier also, Ising Hamiltonian is the one in which you have the sigma I, sigma j. So the system we have which we have is 1D ferromagnet with Ising Hamiltonian. So your H is essentially summation minus j and summation ij sigma I sigma j. And since in the given problem ij are 1, 2 and 3, so you can write your H to be minus j summation you can write as sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1, and now since the loop is complete, no more terms. So these are the terms. Now since in this problem we have 1, 2 and 3, so these are three different spins, three different independent spins. So if you have two, right, and the spins are like either it can take plus 1 or minus 1, right? That's what it can do. And there are three different independent spin. You can think like the operator one or something like that. So in that case, it will go like each spin can have two state, and since there are total three of these, 2 to the power 3, total number of states will be 8 possible configurations will be there. So now we'll have to see what are the 8 possible configurations and what is the energy corresponding to those configurations. If we can estimate the energy and the degeneracy of those configurations, then we can easily estimate the partition function. So now let's just estimate. So this is, let me just divide it as, so this is one section. Another section will be determining energy, and degeneracy. Let's go. So the one configuration which can be there, you can think like all the spins are same, sigma 1, sigma 2 and sigma 3, all the three are same. So let me make a table, then you will get it more better. So this is sigma 1, this is sigma 2 and this is sigma 3, right? And on the right I will write the energy, and this will be states. So let me write it, state 1, in which sigma 1 is 1, sigma 2 is 1, sigma 3 is also 1. Now the second number state, and the sigma 1 is minus 1, sigma 2 is minus 1, and sigma 3 is uh, minus 1. Okay. Now third case, or I can have it slightly better. I can have it to be like this. Now the third case, which will be, I can have it to be, let's say, all negative, all of them to be negative. Right? So the case which can, the possible case which can I can have is like all positive and all negative. Then I can have plus 1, minus 1. Then I can have 1, minus 1, 1. Then I can have minus 1, 1, 1. Then I can have minus 1, minus 1, plus 1. Then I can have minus 1, plus 1, minus 1. And the final one I can have it to be plus 1, minus 1, and minus 1. So total 8 states are there, right? So the total possible configurations are 8, and I have written all the 8 configurations here. Right? So all the 8 configurations I have written. So let me just make it slightly shorter because I'll need it for the energy computation. So just I'll make it shorter in the dimension. Maybe this is good. Same thing I'll do for here also. Yeah. So this is sigma 1, sigma 2, sigma 3. But now if you look into the Hamiltonian, it is sigma 1, sigma 2, sigma 2, sigma 3, and sigma 3, sigma 1. It's multiplication. So let's write the energy, the column for energy. So the energy is minus j sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Let's just compute the energy now. Okay, for the first case, all are positive, so it will give you minus 3j. All are negative, that will give you also minus 3j. If first and second are positive, so sigma 1 sigma 2 will be, okay, so let's write minus j, sigma 1 sigma 2 will be plus 1, sigma 2 sigma 3 will be minus 1, sigma 3 sigma 1 will be minus 1. So this will be plus j. Similarly for this one also it will be plus j. For this one also it will be plus j. For this one, now comes the bottom part. If I compute for this one, it will be minus j times minus sigma 1 sigma 2 minus 1 times minus 1 will be plus 1, minus 1 times plus 1 will be minus 1, and minus 1 times plus 1 will be again minus 1. So this will be plus j. So this also plus j, and this is also plus j. So the basic saying is that for these two states, the energy is, for these two states, the energy is minus 3j, and for all these 3 and 3, 6. So we can say that two states are having energy equals to minus 3J, and 6 states are having energy equals to plus J, right? And that, what does it mean? If two states have the same energy, it means degeneracy of 2. And in this one, 6 states have the same energy, it means it has degeneracy of 6. Okay. Now let's write the partition function. Now we know the energy. So let me just summarize it. Energy times degeneracy. Energy is minus 3J. Degeneracy is 2. Energy is J. Degeneracy is 6. That's what it means. Now based on this, we'll have to write the partition function. Estimating partition function. So if you are given energy and degeneracy, then remember partition function Z is written as equals to summation over all the states e to the power minus beta ei, where beta is 1 by kBt, kb is Boltzmann constant, and T is the temperature, and ei is the energy of the states I. So now I can write it as energy for the one state is minus 3J. So I can write it as e to the power minus beta. Energy is minus 3J. Then another state is there which also has the same energy minus beta minus 3J. Right? So this I can write as 2 times e to the power minus cancels beta 3J. Right? That's what. So what does it mean? The degeneracy came in front. So I can write like this. So the other part also I can write to be 6 times e to the power minus beta j. Right? So if I just summarize it, it will be 2 exponential 3 times beta j plus 6 exponential to the power minus beta j. So this is the partition function. If you have 3 spin states based Ising Hamiltonian system, in which if you have to estimate the partition function, that's what the partition function will be having the form of. If you have any question or doubt on this one, you can ask me in the comment section or by raising the hand. I'll be happy to address your question. Okay, so what is the role of the nearest neighbor? In the Hamiltonian, whenever you write, okay, so in the Hamiltonian, whenever you are writing this Hamiltonian, you are accounting that, okay, if I have a spin here, it is just coupling to the nearest spin. It doesn't care about what's the spin which is here at this point or at third point or fourth point. You are taking the coupling to be the nearest one. That this spin couples only to its neighbor. Let's say so it couples to either this one or this one. So if it is 1, 2 and 3, so 2 can couple to 1 or 3. That's why the term sigma 1 sigma 2 and sigma 2 sigma 3 signifies. That's what it means. If there is a fourth also, then you won't get a term which will be sigma 2, sigma 4. That won't be there, because then you are not allowing the coupling between 2 and 4. It's just the neighbors, between the neighbors, they can talk to each other. So every model has its assumption. That's the assumption of the Ising model. Like that the spin, which is in like will talk to the nearest to it, and that's how the system is designed. For itself, 1 1 2 2 and 3 3 is taken 0. Yeah, because they are not it the interaction the spin won't be having with itself, right? This spin, it, okay, 1 1 is not allowed. The reason being, so this state is not affected by itself. This state will be affected by its neighbor, right? That's why 1 1 2 2 3 3 is not there, because how this spin will talk to itself. That doesn't have any physical sense, right? This spin can only talk to its neighbor or next nearest neighbor, the way you define your system. But 1 1 will not be allowed. So does the 2 2 and 3 3. I mean, so if it is clear, then we'll move on to the next question, which will be based on again the magnetism property only. So the question is something which connects the quantum part to the classical part, and what does the how does the system which we derive in through the quantum mechanics and the wave functions and those parameters, those what you call the Brillouin function which we derive for the magnetism, how does it relates to the Langevin function which we have in the classical counterpart? So what is the limit in which we will be having those scenarios? So the question goes like, under what condition Brillouin function bjx, so bjx means is a function b which depends on the parameter j and x, and so the bjx is actually, if I write the form, it is 2j plus 1 by 2j cot harmonic 2j plus 1 by 2j times x minus 1 by 2j cot harmonic x by 2j. So under what condition this Brillouin function bjx reduces to Langevin function Lx. So Langevin function is nothing but Lx is cot harmonic x minus 1 by x. So let's see under what condition it reduces. So the condition it is asking is on j. Under what condition of j Boolean function bjx reduces to the Langevin function Lx. And why it is important? It just though although it looks to be mathematical form, but it has a very deep meaning in the sense that if you increase the value of the j, how does that essentially means the number of the states? How does your system transforms from the classical to the quantum, from the quantum to the classical part, right? If you have many available states and the spacing between them reduces to infinitesimally small, and then you boil down to the classical part, because then you don't have the very discrete states, right? That's the difference between classical and the quantum. In the classical part, the energy is continuous, where in the quantum, the energy is discrete. So, having said that, let's first understand the Brillouin function uh, Bjx. So, the Brillouin function Bjx solution. Brillouin function Bjx describes the magnetization of a paramagnetic system, where individual atoms have a total angular momentum J, and as we saw, it is defined as Bjx equals to 2j plus 1 by 2j quote harmonic 2j plus 1 by 2j times x minus 1 over 2j quote harmonic x over 2j, and where the parameter x is Gj mu b, which is Bohr magneton times magnetic field, by kbt. Kb is Boltzmann constant and T is the temperature. It is a dimensionless quantity, dimensionless quantity, and it describes and it defines the interaction. As you can see, there is a term J and this J mu B and the B magnetic field. So it is defining basically the interaction between the magnetic field and the magnetic moment J, Gj mu B. Interaction of the magnetic moment with external field. And this 2j plus 1 part comes because in the quantum mechanics, when an atom or ion has discrete spin states, it can acquire 2j plus 1, where j is the this quantum number, and the total number of states will be 2j plus 1. But this is about this Brillouin function. Now let's understand the physical meaning of the Langevin function. And if you understand the physical meaning, so understanding the Langevin function. So it also describes the magnetization of a classical system where magnetic moment can align in any direction. So it describes the magnetization of a classical system. And in a classical system, as you know, I don't have to write of a classical system because where the magnetic moments can align in any direction, and for that your function goes as Lx equals to quote hyperbolic x minus 1 by x. So whenever you have to go with something where you have to go from quantum mechanics to the classical mechanics. So what are the key parameters? First, increase the temperature. So what are the things you can do? Because this will broaden the energy level. Broaden energy level. The another thing which you can do always is you take your increase the number of states. And what this will do, if you increase the number of states, reduce the discreteness of the energy. Reduce the discreteness in energy. So let me give an example. Like if you have, let's say, a particle in as we in this periodic boundary condition, right? We have seen this problem. So if you have an electron in a periodic boundary condition, what happens is it the energy of it can take like the values of h bar square, k square by 2m, but k can only take discrete values which are like n pi by a. So it goes as n square pi square by 2 m a square, and in that scenario your dispersion will be, I mean, like this discrete energies you have instead of continuous. Right? Whereas if you see, so this is the quantum part. This part is the quantum. This is quantum E versus K. Quantum part. If you have to go into the classical part, then what you have to do, you just increase the density of the states. So whatever you are having here, keep it like this and add more number of states so that the spacing between the energy reduces and make it. So what will happen? Because of this, now the dispersion is continuous. Classical part. So you can add more of states so that there is no discreteness available and it becomes almost continuous. So now if you see, it's more like continuous. This is discrete. Discrete energy. It's continuous energy. There's a difference. In this case also you do the same thing. So what you do is you take your J, which determines the number of the states, 2J plus 1. You take your J to be very large, and that will convert your Brillouin function to the Langevin function. Let's see how it does. So the question is, in what condition of J Bjx approaches Lx, right? So we know that number of states is 2j plus 1, and if you have to increase the number of states, so if j tends to j is very large, let's say, so j is very large compared to 1, right? It's 2j plus 1. J is very large number. The discrete quantum states of the system becomes so closely spaced that they effectively act like the classical counterpart from a continuous distribution. Like for j greater than equals to 1, right? So what will happen? The term which you have here, which is this 2j plus 1 by 2j. So if j is very large compared to 1, this term will go to 1, right? Similarly, quote 2j plus 1 by 2j will be also 1 times x, right? And if you expand this thing 1 by 2j times quote hyperbolic x by 2j, what will you get is this x by 2j will approach towards 0 for moderate x, right? If j is very large, this will also approach towards 0, this term 1 by 2j, and you expand it, and if you expand it, you will get to be 1 by x. So under those conditions, 2j plus 1 by 2j will approach towards 1, right? And x by 2j, whatever is the 0, will approach towards 0, right? For moderate x. So the term which is minus 1 by 2j, so term minus 1 by 2j quote hyperbolic x by 2j will boil down to minus 1 over x. Yeah. And that your overall quantity bjx will transform to your Langin function Lx for j very greater than 1. So this is the question regarding where you convert the discreteness of the states to the towards the continuity, and the continuity in the system means in the energy means you are more close to the classical counterpart rather than the quantum part, which is more of discrete energy. If there is any question on this one, you can ask in the comment section. I'll address that one. And if no question is there, then we'll move on to the next problem. Okay. If no question is there, then I'll move on to the next problem, which is again based on the magnetization thing. And magnetization thing which comes from the transcendental equation. So the question goes like, in a magnetic field H, in a given magnetic field H, from the mean field solution. So the mean field theory is the theory in which you take your system and then you uh, take these. It assumes that the whatever the each spins you have, it interacts with the average field created by its local neighbors, rather than considering like any local fluctuations. So what it takes to the a spin is there, then the spin is interacting with a average field environment which is created by its neighbor, rather than just considering any local fluctuations. So that's what this mean field average mean field solution mean. From the mean field solution of Ising model, the leading order correction to magnetization M at the critical temperature Tc is equal to Z J by Kb is. So what it is asking is like, how does M depends on H at the given Tc. So that's something we'll have to determine. So there's a transcendental equation which relates this parameter, this parameter beta, this partition function Z, and the magnetization M uh, to the magnetization and how it will show up. Yeah, I can see the uh, raised hand by Mansi. Yeah, you can ask in the comment section, Mansi, the question. Is there any question? Or I see. Okay, maybe some internet issue. So okay, let's move on. So for the transcendental equation. Oh, M is, you can follow the class notes for this equation. So it has been discussed in the class by the professor again. So it will be 10 hyperbolic beta and JZM plus H is the this magnetization, and this is 10 hyperbolic. You should remember this hyperbolic is different than compared to this magnetization. This magnetic field H. So if you take the 10 inverse on the both sides, so what you receive is 10 inverse M, 10 hyperbolic inverse M and hyperbolic inverse m equals to beta times z JZM plus H magnetizing. Now we expand this parameter. If we expand it, what we will get will be m cubed by 3 plus all the so on higher order terms, which equals to beta ZJM plus H. So if we segregate the terms and just see it in terms of H, what we will get will be 1 by beta m plus m cube by 3 minus JZM, right? And we know that beta is 1 by kBt. Let's replace it here. So what we will get will be kBt times m plus m cubed by 3. There are higher order terms also, which are m to the power 5, m to the power 7. All those terms are also there. JZM. So let's take the term which are prefactor of m. So kBt minus Zj plus kBt times m cubed by 3. So at the given, it has given in temperature Tc, and Tc is Zj by Kb. So if you at T equal to Tc, Zj by Kb, this term goes to 0. So the first term is 0, the second term only remains with higher leading terms also. So kBt m cubed by 3, and if I see m in terms of h, what you will write? I will write 3 by kBt times h to the power 1 by 3. So m is directly proportional to the magnetic field to the power 1 by 3. The magnetization is equals to the magnetic field to the power 1 by 3. That's what it means at the critical field. T is equals to Tc. So if there is any question on this one, you can ask in the comment section. And if there is no question, then we will move on to the next problem statement. Okay, if question is not there, then from following the same question, following the same question, following the same question, and away from critical temperature Tc, so the temperature T is away from critical temperature Tc. Right? The how does the variation of susceptibility depends on the temperature? How does variation of susceptibility depends on temperature T? That's the question. So we know the susceptibility, right? The magnetization M is equals to chi times H, right? And this chi is nothing but the this susceptibility H is magnetic field, M is magnetization. So if we have this equation with us, and now let's follow this equation. So TC is this thing, right? Zj by Kb. So uh, if TC is Zj by Kb, I can just take out Kb in common and can write. So let me just give this equation a name. Let's give equation A. So following equation A, what we have is H is equals to M KBT minus ZJ plus KBT M cube by 3. Right? And EC is equals to ZJ by KB. So, but since in this condition we will be away from TC, the first term will not go to 0. You can take M and KB to be the out, and this becomes T minus TC plus KBT M cube by 3. Now let's remember this formula. To estimate the chi, we'll have to take derivative of M with respect to H. So what we need is uh, del H by del M. If I take, it will be KB T minus TC plus KB E M square by 2M square by 3. If it is 3, right? So it will cancel out 3. KB T M square. And since at, as critical temperature approaches like near TC, M will go to 0. So M tends to 0. So this term vanishes. And in that case, the susceptibility del H by del M is KB T minus TC, and which is inverse of susceptibility. So susceptibility goes as KB. So basically KB T minus TC to the power minus 1. That's how it goes. T minus TC to the power minus 1 it goes. There's a dependency of this magnetic susceptibility on the temperature T and the critical temperature TC. Sorry. Okay, so this I am talking very close to TC, right? This I am talking this uh, T very close to TC. So if you see near the critical temperature TC, the magnetization of the system vanishes, right? That's what happens, right? And your magnetization mean your parameter M. Your M goes to 0 near those temperatures. So I take an assumption near T is equals to TC. In that vicinity only, it's right. Other than that, you are correct. The second term will be there. But since I'm talking near the vicinity of T equal to TC, that's why the second term is vanishing. So if it is clear, then we can move on to the next question, or we can discuss this one also. So this temperature, I think in your, is something which we read in our 10th or 11th class books also, and this is something we also call the Curie temperature. And I think for iron, it's 600 and something centigrade. So if you heat it above that, it's non-magnetic, and if you just cool it below that, it becomes magnetic. So because of thermal energy or Helm's interaction, this magnetization goes to zero. If it is above T is larger than Tc, then in that case it happens. So this is not only near T equal to Tc, this is larger than, if T is larger than Tc, in those scenario also it is always true, because then you don't have magnetization in the system. The thermal smearing of the states, let's say these are your states, the spin, if the thermal energy is large enough, larger than your critical temperature, then what will happen? These spins will fluctuate, right? These spins will fluctuate, and in that case, you won't be having the magnetization. Magnetization comes because you have a certain alignment of the spin in a particular direction. That if your thermal energy is large enough, then you won't be having the magnetization, and your M will go to uh, approach towards zero. So when your T is greater than equals to Tc, this is the case. For T less than equal to Tc, this magnetization term will be there. Yeah, if you have any question on this one, yeah, we can discuss this one also. You can type it in the chat box. So what I was saying in the summary is below Curie temperature, Tc, finite magnetization is there, will be there. So M is not equals to zero. Above Curie temperature, that's how you define the Curie temperature. Thermal energy is more. Thermal energy means KBT energy. Thermal energy is more than the spin energy of the system. Spin energy means the alignment basically system, and that overcomes this spin part, and M tends to zero or M is equals to zero. Both are the cases. That's why for T greater than Tc, M goes to zero. Let me just check for iron. I was saying, let me just check the Curie temperature of iron also. Iron. It's as I was saying, 600 something. It's actually 770 degrees centigrade. Iron Curie temperature. 770 degrees centigrade. So what will happen if you have a magnet? Basically, this is something you can try also. So if you have a magnet and you have an iron, if it is below, if T, and it is a temperature T. So if T is less than 770 degrees centigrade, magnet will attract iron. Right? This is the case at room temperature. When we take our magnet and we keep it near to the iron, it pulls the iron, and we feel the force of attraction between the magnet and the iron bar or any metallic system. But if if you heat your magnet, if you heat your iron above 770 degrees centigrade, magnet will not attract or repel the iron. What does it mean? So iron will act like as if it is uh, not a ferromagnet, uh, even not a paramagnet. So the mean, what does it mean is like if you are above Curie temperature, below Curie temperature, then if you bring your magnet, your spin aligns. This is your magnet. So your spin aligns below T equal to Tc. That means M is not equal to zero. Magnetization is not equal to zero. But if you have a system where T is greater than Tc, in that case your spins will be like randomly oriented because of the thermal energy. And since your M is equals to zero in this case, your magnet will not attract or repel your iron. That's why we took the second term to be zero if we take the temperature to be larger than Tc, greater than or equal to Tc, then in all the cases your M will be zero. Is this clear? Okay, if this is clear, then why the second term is zero, then we can move on to the next problem. Not only the second term, the higher term will also come, right? This is m cube, but there will be m to the power 5, m to the power 7. All those terms will be zero because your m will go to zero. So only the term which survives is this first term, which don't have the m in it. So there is no m in this box, right? That's why this term survives. It goes as inverse. Susceptibility goes as inverse of the temperature. What do you say? So I will take maybe one or two more questions, and then we will conclude the class after. So I think two more questions. So the question is, if there are states given in the systems, and if those states operate on a given, uh, there is an operator which operates on those states, then what will be the outcome? So basically determining the eigenvalues of that system. So, like if the operator operates on those eigenstates. So the first state is you have the four states: up, up. It's a two-spin system in which it can have either up, up state, down, down, up, down, and down, up. So the first state, so here you can think it like to be A, B, and there are these operators, which is A will be, let me call to be the 1Z, and B will be 2Z, right? In that they will be that in my case. So operator is operator in my question is half minus S1Z, that will operate on the A part, the first part basically spin, and then you have half minus S2Z. So the S2Z will operate on the second part, like this, and this second. And then we'll have to estimate what is the expectation value. So if S1Z operates on a spin up, it gives us the half. And if it operates on the spin down, it will give minus half. That's very obvious. Similarly, S2Z, if it operates on spin up, it also gives the plus half. And if it operates on the minus, on the down spin, it will give the minus half. Or let me better write, instead of 1 or 2, Sz operates on up spin, it gives plus half, and if Sz operates on down spin, it gives minus half. That's more clear. And we'll have to estimate the values if this operator operates on the above given four states. So case 1, this operator S1z 1 by 2 minus S2z operating on up spin. So let's first solve this one, because then we'll be using this one for all the four cases. So it will be 1 by 4 minus 1 by 2 S1z plus S2z and plus S1z S2z, and this full work operates on the up spin. So 1 by 4 or acting on this will give you the direct 1 by 4 minus 1 by 2. If S1z operates on this one, so it will operate on the first part. So first part will give you half. S2z will operate on the second part, which will also give you half. Plus S1z, S2z will operate on the first and the second part, that will give you half times half. So this is nothing but 1 by 4 minus 1 by 2 plus 1 by 4. That will give you 0. The eigenvalue of this one is 0. Similarly, case 2. This is how you determine the eigenvalues of a if an operator operates on a given state. That's how you determine the value. What will be its value? So it's 1 by 4 minus 1 by 2 S1z plus S2z plus S1z S2z operating on. So up is over. Now we'll operate on down down. Down, down. So on down it will give you minus half whenever it will operate. So 1 by 4 times this will be 1 by 4 minus 1 by 2. S1z is operating on this one will give you minus half. S2z operating will give you minus half. S1z, S2z will give you minus half times minus half. So this is essentially 1 by 4 plus 1 by 2 plus 1 by 4 acting on spin down down. That will give you 1 times spin down down. So this will give a value of 1. Similarly, case 3. In that one, will operate on up down. 1 by 4 minus 1 by 2 S1z plus S2z plus S1z S2z operating on up and down. So that gives you 1 by 4 minus 1 by 2. S1z operating will give you plus half. S2z operating will give you minus half. Plus S1z S2z operating will give you plus half times minus half. And down. So it is 1 by 4 minus 0 minus 1 by 4. And that will give you 0 operating up and down. Similarly, case 4 you can try. So the case 4 is also the same one. It's 1 by 4 minus 1 by 2 S1z plus S2z plus S1z S2z operating on down spin, up spin. So this will give you 1 by 4 minus 1 by 2. S1Z will give you minus half. S2Z will give you plus half. S1Z, S2Z will give you minus half times plus half. Putting on down spin and up spin. So this gives you again 0. So only if it operates on down spin, it gives value of 1. Otherwise, all the time its value is 0. 0, 0, and 0. That's how you calculate. If an operator operates on a state, what will be its value? So that's how you estimate the eigenvalues of it. So if this is clear, then if any doubt is there, you can ask in the comment section. This problem, and if not, then I will move on to the next question. So I'll draw a figure. Meanwhile, if you have any doubt, you can ask in the comment section. So the question is, drawing. So this is 1A. Then I will draw B. So B is something like this. In the right color only. This is up, this is down, and this is question mark. So A and B are over. So here length of arrow proportional to the magnetization strength. Okay. Now based on this, if I ask you which of these is under what category do they fall? Which of this is ferromagnet, antiferromagnet, canted antiferromagnet, frustrated antiferromagnet, or ferrimagnet? So what are they? Like if I ask you about A, is it a ferromagnet, antiferromagnet, frustrated ferromagnet, frustrated antiferromagnet? What is this A? Can anybody answer? Yeah, correct. Yeah, Mansi responded, and it's the correct answer. It's an antiferromagnet, and the reason is very obvious. If you have spin up here, the next neighbored spins are opposite to it, down. Then, if you see in the reference of this spin, it's up, And let's say if you take the middle one, this is up spin, then this is down, 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 and down. But if you take this one, the neighbor are just opposite. They cancel the net magnetization, and these kind of the system we call the antiferromagnet. Antiferromagnet, correct. What about the B? Under what category do this fall? So let me just write here. Partially ferromagnetic. Uh, uh, these systems are, like, of course, will be partially ferromagnetic, and so some magnetism will be there, of course, because whatever you put, either you put here spin up or spin down, whatever you put, it will be having going to have a net magnetization. But these type of systems, actually, whatever you put, up spin or down spin, right? If you look in the reference of this one, you should put the down spin. But if you look at the, then you want to put the up spin. So it's frustrated system, and that's why these type of systems are interesting, because they have a very different origin, and they bring the different kind of class of physics because of their unique magnetism, and they are categorized under frustrated antiferromagnetism. So if you see here, this is up spin, this is down spin, then it's an antiferromagnet type. But here, whatever you put, it won't be a perfect antiferromagnet. That's why it's a frustrated antiferromagnet. And this is antiferromagnet. The first one is antiferromagnet, of course, with the obvious reason that the neighboring spins are opposite, aligned, cancelling the net magnetic moment. Now coming about the third system, here what you see, it's similar to A, but differ in the sense that the arrows which are pointing in the direction which is upside has different length compared to the arrows which are pointing downside. And since it's defined that length of the arrow is directly proportional to the magnetization strength, or magnetization basically, then what will be this system called? The C. What this system C will be called? Any response? I think Mansi is typing in the chat box. Let her type it. Depends whether the pointer with the larger length point in the external magnetic field lies on a positive field. No. See, the magnetic field comes later. What does the magnetic field do? To magnetic field aligns. If you put these states in the magnetic field, then this antiferromagnet can also turn to be the ferromagnetic. Because if you apply large enough magnetic field, whatever the arrows which are pointing down, they can also point up, and then everything will be pointing up, and then it will be a ferromagnet. That's the effect of the magnetic field. But if you don't put your system in the magnetic field, it's in the zero magnetic field, and you look at the system, how the spins are aligned in the system, then we talk about the system and describe the system whether it's a ferromagnet or not. So in this case particularly, if spins are aligned like antiferromagnet, right? Opposite. If this is up, this is down, this is up, this is down. This is what we call antiferromagnet. But their magnetization M1, let's say this for this one, let me call this is M1, this is M2, again this is M1, this is M2. If M1 is not equals to M2, right, then it is called ferrimagnetic. Then it is called ferrimagnetic. So these are the different, looking at the spin arrangement in the system, you can tell which will be antiferromagnet, which will be frustrated antiferromagnet. If the magnitudes are different, then it will be ferrimagnet. So all this is all about this and today's class. If you have any question or doubt in this one, you can ask in the chat box or in the comment section where you want. I'll be happy to address it. Yeah, book, like as I said, that the book is you don't have any better book than the Charles Kittle, and Charles Kittle is there. Charles Kittle, and the another book which I prefer is let me just I'm forgetting the name. Ascroft Marmin. Yeah, I remember the name now. Ascroft Marmin. Maybe just since I have now have the message in the chat box, I will upload the soft copy of those books. Of course, those are not the. I mean, I will upload the soft copy of those books in the channel, and then you can download the books and can. I will look at the problems based on this. So these are the go-to books to understand the basic electronic theory of solids and the condensed matter. And I do recommend reading these books, even if you complete this course. After completing this course, also, if you want to be like in touch with the condensed matter part, you should read these books very thoroughly. Maybe not once, not twice, multiple times, as much as you can. And if this is clear, and if no more questions are there, then let's close this session, and we will meet on the next Saturday, same time, 6:30 p.m. 6 p.m.